So obviously I can't actually use computers because somehow there's no audio from the recording from last lecture. So I'm going to re-record it so that we have a record of it. So in the first lecture, we got up on this point where we defined a record type representing pairs of elements from A and B. So because it's a record, in order to give an inhabitant of this type, we have to give something of each field. So it has to be an A and there has to be a B. And then we had this pattern matching definition, which said that, well, if you have one of these, then you can produce another one in a different order. So that's one way to say, okay, I have A's and B's and I want one of each. But sometimes you want to have an A or a B, for example. And then the record declaration here would not be suitable because this really says you have to have all of the fields, right? But if you rather want to have a choice of an A or a B, then we can do that with a so-called sum type. So we're going to declare this not as a record, because record means have all of the fields to be happy, but rather as a data type. So I'm going to say data, and then here's the name of the type. And again, I'm going to have two parameters, A and B, which are sets. So they go where the underscores go. And then we have this actual name of it, which is a type with a backslash u plus. So it's a funny little u with a plus in the middle. And that's the traditional name for this sum type. It's like a union. Okay, so we have two parameters, and this is going to give us a new type. So I'm going to say this is a set. And then I say where, and here, a little bit indented, I'm going to list all of the possible ways to make an element of this type. So I'm going to list all of the constructors. So in this case, I want this to be a sum type. I want to be an A or a B. So I'm going to have two different constructors. And in the standard library, these are called ing1 and ing2 for injection. And this little one I type with a backslash and then an underscore. And then down here at the bottom of the screen, I can see all of the things I can continue with. And in this case, I wanted a subscript 1. So I picked that one. If I wanted a subscript A, then I would do underscore A and so on instead. Okay, so I want my first constructor to be called ing1. And this one should inject an A into my sum of A and B. So I say A goes to A u plus B. And I could also have a second kind of injection, ing2, which injects a B into A times B, right? So I'm saying I'm declaring a new data type, the data keyword, and it has two constructors called ing1 and ing2, and these are the only ways to make one of these, right? So in Haskell, you would still use data, you wouldn't use any fancy Unicode, and you wouldn't explicitly give the type of the constructor, you'd just say ing1 of A, for example, just listing the arguments of the constructor, but not the full type. But here in Agda, we are actually writing out the type of the constructor, right? And the idea is that in order to make one of these, you have to do it with one of the constructors. And one way we can see how this plays out is if we now try to write a function out of one of these. So it's a u plus, and we have instantiated both A and B to be C. So if I have a C or a C, I should be able to get the C out, right? So let's see if we can write this. So I say reduce equals question mark, because this is the thing I want to define. I don't quite know what I want to put here yet, so let's do it slowly. I reload the file. I can look at the goal. Make this a little bit bigger. So you see that my current goal is to make a function from C or C to C. Okay, so because that's a function, I can introduce an argument here on the left. I'm going to call it x. I reload the file. I can look at my new goal. And I see that my goal now is to produce the output of the function, the C, given that I have an x, which is a C or C, right? Okay, so how can I make progress? Well, I don't know exactly what x is yet, but I could inspect it more by pattern matching on it or casing on it. So I go into the goal, I do Control C for case. Agda's asking me, what do you want to case on? And I want to case on the variable x. And then I press enter. And then where before it said reduce of x equals something. After I do this, the x has been split up into all the possible cases. And because there are two constructors of the data type, there are two cases here. It's just either a left injection or a right injection. So we can look at what we need to do here. So here we still have to produce a C, but now because the case I'm considering is the case when the original x was a left injection, then the x I have here, I could rename it into y just to make it a bit clearer. The y I have here now is actually a C, right? So that's the one I can return here. Similarly here, if I had a y coming from the right, then again, that has type C, so that's the C I can return. So I'm basically saying, well, there's two cases. It could either be a left injection or a right injection. And in both cases, the thing that has been injected is the one I return. Right? And notice that I had to cover all of the possible constructors here. And when I did a case split, then Agda made sure that I covered all the cases. But if I wrote it by hand, or if I comment out one of the lines, for example, then I get an error that is incomplete pattern matching. And the case ing2 of something is missing, right? So that's an error. And also you can see up here that the function which has incomplete matching has been highlighted in orange. So Agda is not happy if you're not covering exactly all of the cases. Whereas in Haskell, you could just write it like this and it would crash at runtime if you try to give it one of these. Right? But here we're trying not to crash at runtime and use the types to make some guarantees. Right? So that's one data type. And it's one of the simpler ones because we're just saying there's a finite list of choices and then we are referring to types that already exist in some sense. Right? But we could also make a so-called inductive type where we're also having the constructors refer to the same kind of thing as we are defining. So the typical example of this is the natural numbers. So the idea here is that a natural number is either 0 or it's the successor of another natural number, right? And this way I can get 0, then I get the successor of 0, which is 1. We get the successor and the successor of 0, which is 2, the successor of 2, which is 3, and so on. And this way I can get all of the natural numbers, right? And these are exactly the natural numbers. So we can model this with a data type. So I say data again. I'm going to call it Blackboard N, which I type with a \B for Blackboard, capital N for N. Okay, and I'm going to say that this is a type. That's just a set. There's no parameters this time, right? It's just the type of natural numbers. Then I say where, and again I list all of the constructors. And I said there should be 2, there should be 0 and successor. Start with 0. Okay, 0 is just a natural number. Don't have to give it any arguments. It just is. And then we have suck, which if you give me a natural number, suck is going to give you back another natural number, which you think of as 1 greater than the one we were given, right? So then we have suck of 0 and suck of 0 and so on. And because it's quite annoying to say suck of 0 if you want 9 or whatever that was. There's some special support for the natural numbers if I use the built-in pragma. So now if I do this, then I can say that I have a natural number, and rather than saying suck of 0 and so on, I can actually just say 2, for example, in decimal. And Agda will also print things out in decimal. It can sometimes be helpful, right? Okay, let's have a variable block. So if you're mentioning M and N without introducing them explicitly, then I'm just going to assume that they are natural numbers now. It can sometimes be helpful. Right? Okay, so let's write another function. So we have the successor function as a constructor. So that's just a thing that is, right? It's how you build natural numbers. So if I give it any natural number, it's going to give me another one. And it's going to be a new one because it's a constructor. But we could also try to define the predecessor function, which if you give it, say, 17, it should give us back 16 and so on, right? So let's do that. You can say pred of x equals something, as we always do. And then we can look here, see that we want to give back a natural number. We have a natural number, so we could give back x. That would be type correct, right? But it wouldn't match the spirit of the function we want to define. So I want to say I wanted the predecessor, not the identity function, right? So in that case, I can't just give back x because that would be the wrong thing. And without looking further at x, I can't really tell what to give back here, right? Because if x is 17, then I should give back 16. Whereas if x is 5, then I should give back 4 and so on. So I give back different things depending on what x is. So that suggests to me that we should try and k-split on x again. Okay, then we say we have two cases. And let me rearrange them, because this is the interesting one, right? If we have a successor as our x, let's call it suc of n, then the predecessor is this n, right? Because this is representing n plus 1, and the predecessor of n plus 1 is really n. So here we can get back the n. And then here for 0, we can't really say -1 because we have just the natural numbers. So we have to have some kind of default values. We could get back 0. And we could also say just anything like this. So how is this going to work? Well, we're going to go through these equations line by line and see if they match. So for example, if we want to compute predecessor of 16, then because 16 is the successor of 15, when we're trying the first line, then this is going to match. So 16 is suc of 15, and we're going to return 15, right? And it doesn't matter that this line will also match, because we have a first match semantics, which means that the first line that matches is the one that will work. So we could try this either by doing well, there's two ways we could do it. I could define a test, which is a natural number. I can say that this is pred 16. Okay, so that tells me that the type is right, but if I actually want to know what this computes to, then I can use Control-C, Control-N for normalize. And then I type in an expression, in this case test, and 15 comes back, right? But of course, I don't have to name it to do this. I could just do Control-C, Control-N directly, and then say pred of 42 is 41, right? Okay, and if I now try pred of 0, then I get 0, because the first line does not match. 0 is not a successor. Then we go to the second line, and pred of 0 then must be 0, right? Because this line matches anything. Okay, let me delete that again. Right, so that way you could define a different name for 0, pred of 0, but it will just compute the same thing. Right? Okay, so let's define another function called iterate, where we do another kind of pattern matching. So we do it the usual way. I want to define something. I don't know what it is yet, so I'll say it's equal to question mark. Okay, and well, I'm defining a function, so I might as well introduce all of these arguments. I could do it with refine, and then I can move them to the left, and then I'm going to rename them anyway, so I know what they are. The first one is a natural number. I'm going to call it n. The second one is a function f, and the third one is a kind of start value. Because what do I want this function to do? Well, it's called iterate. So the idea is that I get the number n and a function, and I'm going to iterate this function n times starting from this value. So if I iterate it 2 times, I want this to be f of s. If I iterate it 17 times, it should be f of f of f of f of f, and so on 17 times, right? So in order to compute what this should be, I think I have to look at the natural number again, because I'm going to give back different things depending on how many times I want to iterate it, right? I'm going to do a k-split on n. Okay. If I'm iterating it 0 times, that means I should not apply the function. So I can just give back the starting value, f of s. And if I'm iterating it suck n times, well, that means that I'm definitely doing at least one time, right? Because there's a suck. So it's going to be f of something. Okay, and then I have to figure out what the something is. It should be an a again. Well, if I iterate it n times after this, then in total I've done it n plus 1 times. Right? So I can do a recursive call, iterate nfs. Okay. So what's going to happen if I do iterate, say, 2fs? Well, then it's going to be f of iterate 1fs, which is going to be f of iterate 0, fs, which is going to be f of s, right? So 2 times f, that seems to work. But why is this a valid definition? How do we know that this is not going to run forever? And the reason this is okay is because we're doing a call to the same function, but only on a smaller argument, right? So we started off with suck n, and then the recursive call was on n, which is smaller. If I try to do a recursive call on suck n again, then if you imagine what's happening, we're just going to keep calling ourselves forever, over and ever, right? It's going to just be f of f of f of f of f of f, and this is never going to go down. If I try to do that by reloading, then Agda is complaining that it can't figure out why this is possibly terminating. Rightly so, because it's not terminating in this case, right? And Agda is only happy with functions that are definitely terminating. So it has a built-in termination checker that checks if things are terminating. And of course, checking if a function is terminating is impossible to do in general. So what we have here is necessarily an approximation of this. And the approximation says that you're allowed to do recursive calls on these inductive arguments as long as the recursive call is on something which is a direct subterm of the thing. So that's why I change this back to an n here. It's okay again, because n is a direct subterm of suck of n. It doesn't have to be direct, but it has to be a subterm. So it wouldn't be okay to, in general, to say 0 here. I think it's clever enough to see that this 0 case actually, you could try it. Yeah, so that's okay because 0 is not doing a recursive call, but I couldn't do n minus 5, for example, because that's not a subterm directly of this. Right. Okay, but I want this n here. So it's necessarily a bit stupid because you have to be a bit stupid if you're a computer trying to do termination checking, but most of the time it's okay. And there are ways to do what you want with a little bit more work, but hopefully we won't have to do that for a while. But the basic idea is you try to write your function, recursive calls are okay, as long as they're on smaller things. And if Agda is happy, then you can be happy. If Agda is not happy, then you can start worrying about it. Okay, so let's also define addition as another example of a function. So what is addition? Well, this should be something that takes 2 natural numbers and gives us the sum, right? So the type should say, well, you give me 1 natural number, you give me another natural number, and then I'll give you back a natural number. Again, we have the underscores of where the arguments go, right? Okay, so let's see if we can define it. Say n plus m equals something. Okay, and we don't really know what this should be without looking at n or m, right? But now we have a choice. Should we look at m or should we look at n or m? And in this case, actually, there is no good choice, or rather there's 2 good choices. It doesn't really matter which one we look at. So just to follow the standard library, I think we should look at the first one, but it would work equally well to look at the second one. So I'm going to do a case split on n. And Agda says, well, you have 2 cases. N is either 0 or a successor. And just to make it a bit clearer, I'm going to put in these brackets, even though because Agda wrote it, they are not strictly necessary, but I think it makes it a bit easy to read. So we have these 2 cases. We have to say what is 0 plus m and what is suck n plus m, right? Okay, so 0 plus m should probably just be m. Okay, and suck n plus m. Well, what is this? So this is n plus 1 plus m. And by this termination criterion, we are allowed to do a recursive call on n and m because n is smaller than suck n. So I know that n plus m is something. It's a natural number. So I can do that. But if I just give back this, then if you imagine what's going to happen, if I then we're just going to peel off the sucks, and we're going to eventually get back down to the base case, and we're just going to return the second argument, right? So that's not right. But we could put a suck on the outside here. Then we are preserving the numerical value of this, right? This is n plus 1 plus m. This is n plus m plus 1, which is the same thing. But the recursive call is on something smaller. So we're moving the suck to the outside. So we could, again, just try and do Control-C, Control-N, and say 5 plus 7, and we get 12 back. So that's reassuring. Right. And then here's also a challenge that Guillaume has left for you to not do this by pattern matching, but use the iterate function instead. Could be fun. But instead, let us move on to actual dependent types. So remember that up here in the beginning, we had the record type of pairs of a value from A and a value from B. Right, so I'm going to copy this. And put it in here. And now I'm going to rename it. So for traditional reasons, this is called a sigma type. And the idea is that I'm still going to have a value from A, but then the type B itself is going to be allowed to vary depending on which value I picked for the A. So it's a so-called dependent type because depending on the value of the first argument, B of A could be a different type. Right? So A is a type, and B of A is a type for every A from big A. So B of X is a type for every X of type A. So we can really refine what it means to be in the second component of this pair, depending on what the first one is. So that's also why it's called a sigma, because a sigma is like a sum, which is like a choice. So we can choose what the second thing could be depending on what the first one is. So I still want to have these two projections, but so it makes sense that I have something of type A, but now I can't say I have something of type B anymore because B is not a type in itself. It's only a type if you give it an A. But thankfully I have something of type A. So I can say B of the first projection, that's a type. So it makes sense to ask for something of that type, right? So this is a typical dependent type where the type of the second component in the field really depends on the first component. And we can't really give any good examples of this at this stage because we have no other dependent types. We have no examples of these things, but we're going to introduce something very soon. But you could imagine saying, I want to have a natural number such that that natural number is greater than 17, for example, right? That's a typical example of a dependent type. So the A is not, and B of X says that X is greater than 17. We're only happy with these ones. So you get a really precise type this way. So let's see if we can introduce this typical example of a dependent type, which is equality type. So I'm going to call this triple equals. And again, this is going to be a data type. To say data. And the name of it is triple equals, which you get by typing backslash equals equals. It would be nice if you could just call it normal equality, but you can't because that's already used by these kind of equations, right? So, okay, so this is the name, and I'm going to have a bunch of parameters. First of all, it's going to be a type A. Then there's going to be some left-hand side of type A, and there's going to be a right-hand side, which is also type A. And I've declared this thing in curly brackets to make it implicit, which means that I don't have to mention it. Agda is going to figure it out for me. So this says that if you have little a of type A and some other a, then the type A equals B is a type. Doesn't mean that A is equal to B, it only means that if we can give an inhabitant of this type. So how can we ensure that? Well, it's a data type like everything else. So we are going to give the constructors, and it's going to be exactly one constructor called refl, which says that, well, it's okay to say that A and B are equal exactly when B is the same as A. So I'm going to say A equals A. So the A here is the parameter from here. And then in theory, I can choose whatever I want for the second A, but I'm going to choose the same parameter. So the only way to construct something of this type is to really have A equals A. So they have to be the same, right? It's called refl for reflexivity, because that's the property of being equal to yourself. Right. So I load that, and I accept that. So now, for example, I can say that 17 equals 17. And what's the proof of this? Well, there's exactly one constructor, and it's called refl, right? So I reload it, and we see that Agda is happy. So what we've done is we instantiated the type A with the type of natural numbers, and we instantiated the little a with 17. So we see that refl for that A indeed has type 17 equals 17, right? If I try to change this to say 16 and reload, then Agda complains that refl does not match here, because refl has type 17 equals 17, for example, but 16 is not the same as 17, right? I could change this to 16 again, and then it would be okay. But if I change this to 15, then again, it doesn't match, and refl is not, it's not a valid thing of this type. And this was the only constructor, right? Here's another example, which looks a little bit trickier. So we see that we had this notion of composition from the lecture 1, which we define like this. And another way to define this, of course, is to say this is lambda A goes to this. And what we had down here is the claim that if you bracket the composition of 3 different functions in 2 different ways, so you could either do this composition first and then compose with h in the end, or you could do this composition first and then compose with f in the end. The claim is that you still get the same result. And that's a bit surprising, because this does not look exactly like this, right? So here we said it has to be exactly the same A on both sides for refl to work. But here refl works anyway. Why is that? Well, if we remove that and look at what we need to give, then we see that this thing has computed to this particular lambda expression. And similarly, this thing has computed to the same lambda expression. So that's why refl works, right? It's not just looking at the syntax of the source text, it's trying to normalize things as much as possible. So all of this computes to this lambda expression, and all of this computes to this lambda expression, and they happen to be exactly the same. So refl fits here, right? So everything is up to equality, so to speak. It's not just a string of text, but if you define things to be equal to other things, then that will be taken into account. So one striking way you can see how this works is if we try to define substitution. So this is also in the standard library, and it's called subst. And the idea is that if I have a type A, and if I have type family over A, so that's one of these dependent types again, right? So it says for every A, I get the type. And if I have X and Y in A, and I have something which says that X is equal to Y, then if I know P of X, then I also know P of Y. So I'm thinking of this P as a kind of property of A's, and having something of type P of X is evidence that P of X is true, that P of X holds, right? So this says that if X is equal to Y and I know P of X, then I can substitute X for Y in P and I get the P of Y, which is something you would expect of an equality. So let's see, so I've turned this A implicit, so I don't have to mention it. Do have the big P, I have X and Y, and I have a proof EQ that X equals Y, and I have a PX which says that P of X holds, and I have to produce something of this type. Right, so we see that's my goal, P of Y, I know P of X, and so on. Right. Okay, so how can I possibly get the P of Y? Well, I don't have any function that explicitly produces a P of Y. That's what I'm trying to make overall, right? So I probably should try to pattern match on something maybe. And the only thing I can actually pattern match on are data types, right? The only thing of a data type I have available is this proof EQ, because this was defined to be a data type. So I could say, okay, what could this proof EQ possibly be that X equals Y? Let's see. Well, there's only one constructor of this data type, REFL. So this proof must be REFL, right? And by pattern matching, we see that that's playing out in the sense that that's the only case we have to consider. Right? But then also something else magical happened, which was that if this must have been REFL, then in fact the Y must have been X, right? Because REFL has the same on both sides of the equality sign. So I pattern matched on EQ. We can go back. I started off with X, Y, and EQ. I pattern matched on EQ, and I ended up with X, X, and REFL. So pattern matching on EQ actually refined everything that's happened here on the left. And I just put in a little dot to signify that this was a forced pattern match. I didn't explicitly pattern match on Y, indeed I couldn't, because I don't know that A is a data type. But by pattern matching on this one, I forced this one to change to an X as well. That's what the dot signifies. And nowadays you don't need a dot. I just happen to put it in silently for you. But if you want, you could leave it as kind of documentation that this was forced. Right? It's called a dot pattern. And the magical thing that really happened now was that our goal used to be P of Y, but we discovered by pattern matching on this thing that Y was in fact X, which means that our goal is actually P of X. And we have something of type P of X, so we can just use that, right? And then if you want, you can notice that, well, this thing here is now just the identity function, right? So we pattern match on EQ, and then we see that it's really easy to go from P of X to P of X when Y has turned into an X. So that's the magic of pattern matching on equality proofs. It takes a little while to get used to maybe, but you just kind of talk to Agda and then it makes sense. So we could do one more example of this, which is called Cong for congruence. And the idea is that every function respects equality. So you might remember from algebra that a congruence is a function that respects a certain relation. So this Cong here says that every function is a congruence for equality, which is again something you would expect, right? Just like you would expect to be able to replace X for Y, if it's really you have know that X is equal to Y, you would also expect that if x is equal to y, then f of x should be equal to f of y for any function. So let's say that, to say that a and b are types, have a function from a to b, and now if I know x and y are in A, I know that x equals y, then I also know that f of x equals f of y. Okay, and then with a little bit of experience, you realize that we probably don't need to mention the x and the y explicitly here, so I'm going to make these implicit as well. And it's a bit tricky because when you define a function, then if you're not going to pattern match on something explicitly, then you could think that you could make it implicit, but you also have to remember that when you use the function, Agda needs to be able to figure out what these implicit arguments are, right? So there's a bit of an art or a science to determine what can safely be made implicit. And if you get it wrong, then Agda will just color your call site yellow, and you have to explicitly give it, or you can go back and change it. So the general rule is that you can make things implicit, so use these curly things and not mention them, if they are determined by the other arguments. So in this case, if you have a proof of x equals y, then that is going to determine what x and y are. That's why it's probably safe to make this implicit. Whereas it would not be okay to make this whole family of types implicit in general, because it's really hard to figure out what this whole family should be. It's a function. So you have to determine for every a and a, kind of reverse engineer what the p is, which usually is not going to happen. So that's why I made this implicit, but I didn't make this implicit in that case. Okay, and similarly here, if I have a function from a to b, that's probably going to determine what the a and the b are, so I can make these implicit. But if you get it wrong, then you just get some yellow, and you can go back and change it. But let's see. Okay, so the a and b are implicit. I don't have to mention them here. I have a function f. The x and the y are now implicit, but I have some equality proof eq. And then I have to name this f, right? Because I'm referring to it here, so I have to explicitly name it here. Okay. So we see our goal is to show that f of x equals f of y. And we know that f is a function from a to b, and we know that x equals y. Okay, so you could say, well, the only way I can prove that two things are equal is to give REFL. So I probably just have to say REFL here, right? But unfortunately, that does not work because, like we've said before, REFL requires to have the same thing on the left and on the right. And here I have f of x on the left and f of y on the right. So Agda figures out that it's an f on both sides, but then we would also need the x to be the same as y for REFL to fit here. So it does not fit. Well, that's bad news. But we haven't used all the information we have. So again, we have this EQ available, which says that x equals y. So we could say, what could this EQ possibly be? Well, it can only be REFL. And then the magic has happened again, that if that was REFL, then x must have been the same as y, which means that now our goal has changed by pattern matching on this. And now it looks like REFL would fit much better, right? So I can really give REFL in this case. So I couldn't give it beforehand, but by making more information available by pattern matching on things, I refined the situation. And then I ended up in a case where this would make sense. Right? That's the magic of the pattern matching. Or put differently, I wrote a program, right? Which said that, well, if this is of a, my input is of a certain form, there's only one possible form, in this case REFL, then my output is going to be of a certain form. So proving and programming is basically the same thing in Agda. You can read this as a logical proposition, or you can read it as the type of a program which has this behavior. If you give it REFL, then it's going to give you REFL back, but at a slightly different type. Right? And then here is a fun challenge for you to actually implement this function in terms of subst, which basically means that you have to come up with a suitable p that makes this make sense. Right? And similarly, we said that equality is reflexive. That was basically the definition of this constructor. But you would also expect equality to be symmetric and transitive. So symmetric means that if x is equal to y, then y is equal to x. Transitive means if x is equal to y and y is equal to z, then x is equal to z. So you can do 2 steps in 1 step, right? And this, as you can flip things around. That's something you would expect of equality, so you could see if you could do pattern matching proofs of this again using subst to do it without explicit pattern matching. That's a fun challenge I would recommend. And I think that was as far as we got during the lecture. So we could perhaps just see that indeed things compute. So we already talked about this. But if we want to prove that pred of suc of n equals n, well, we look at the definition of pred, then pred of suc of n equals n is exactly one of the equations. So if we look at what we need to prove here, we see that the goal has reduced to n equals n, because pred of suc of n computed to n, and then here again, REFL works, right? So these computational behavior of things is really taken into account when Agda type checks things, because again, seemingly REFL has to have exactly the same A on both sides, but that's after we have computed as much as possible, right? And a lot of programming in Agda is doing the right kind of pattern matching so that things compute and so that you see how to do the thing. So this was kind of an extreme case of that, right? So that had the pattern match on this REFL before this REFL would fit. But okay, I think this is where we stop.